Welcome to the course Excelling with Mathematical Modeling. Today we will be talking about an economic model, namely Harrod model. So, Roy F. Harrod, he introduced the concept of this warranted growth, the natural growth, and the actual growth. So, the warranted growth rate is the growth rate at which all savings is absorbed into investments. So, he has three variables defined. The first one let's denote by GN, which is called gross domestic product, GDP, or national income. So, we use the word say national income. Then you have savings and you have investment. The savings of the people, investment of the people. Now, the first assumption. Assumption 1. So, the first assumption is in a country, people's saving depends directly on national income. So, the savings depends directly on national income, which will give you Sn is equal to some alpha times or A times Bg, where A is a positive quantity. Assumption 2. Investment made by the people depends on the difference between the national income of the current year and the previous year. Again, depends directly. So, your investment that will depend directly on the difference of the national income of the current year and the previous year. So, this will give you some In is equal to some B times Gn minus Gn minus 1. And finally, assumption 3, let me write it here. All savings made by the people are invested, which means that Sn is equal to In. So, we have these three assumptions of the Harrod model. Now, let us see what it tells about the national income. So, you have Sn equal to A times Gn, you have In equal to B times Gn minus Gn minus 1, and you have Sn equal to In. So, let us start say equation 1, this is equation 2 and this is equation 3. So, from 2 I get In is equal to B times Gn minus Gn minus 1 from the assumption 2. Now, since In is equal to Sn, this is replaced by Sn using 3, and we have Sn equal to A times Gn. So, it is A times Gn equal to B Gn minus Gn minus 1. This is using 1. So, you solve for Gn, and this gives B minus A times Gn is equal to B Gn minus 1, or Gn equal to B by B minus A G minus 1. So, we get a relation between the national income, which depends on the previous year's income, previous year's national income, and you can simplify this a bit. So, I will replace this Gn minus 1. So, if Gn is B minus B by B minus A Gn minus 1, and Gn minus 1 will be B by B minus A Gn minus 2, and so on. So, I will replace this Gn minus 1 by this. So, which will be B by B minus A Gn minus 2. Similarly, B by B minus A, B by B minus A, B by B minus A, Gn minus 3. This can be B by B minus A cube, Gn minus 3. So, if this is 3 and this is 3, so if I replace, or if I go till the n terms, this will be n, and this is n minus n, so G0 and Gn. So, I get that your national income can be written as B by B minus A whole to the power n multiplied by the initial value of the income. If I replace this by some k, where your k is B by B minus A. Let us now see the dynamics of this national income for this various values of k, and we will do it numerically, for which we will be using Microsoft Excel. So, I already have it opened. So, here Gn plus 1 is equal to G0 B by B minus A whole to the power n. I replace this by k, and I get this is G0 k to the power n. So, I put the initial values, say 10 to each of them. We have 4 cases to discuss, which is the values of k 1.5, 0.5, minus 0.5 and minus 1.5. So, the very first case we take where your k is greater than 1, and I take the value to be 1.5, and this is equal to, so if I put n equal to 0, I get the next one G1, which is G0, which is 10 here, multiplied by k, which is a constant, and whole to the power n equal to 0. So, this value is a constant, this value is also a constant, and we calculate till 10 of the values. If I want to plot them, I will get something like this, and let me name the chart title. So, this is the case where k is greater than 1. Okay. So, I will explain this curve later on. Let me first generate them. Now let's k lies between 0 and 1, so which is 0.5. So this is equal to again the initial value multiplied by k to the power n. These two values are constants. And I drag them. So now if I want to solve them, first I highlight this, then I press Ctrl and click this, then I press Shift and click the down cursor. So these two columns are highlighted. Go to Insert, go to the chart and draw this. So this is the case where 0 less than k less than 1. The third one is say minus 1 less than k less than 0. So again the initial value multiplied by k, which is constant, to the power 0. And again if I plot this, I highlight them, press Ctrl, go here, press Shift and down. So insert, go to the chart and this. So some sort of oscillatory behavior. So here it is minus 1 less than k less than 0. And the last one when k is less than minus 1. So again this is equal to the initial value multiplied by k to the power n. This is also a constant and this is also a constant. So just so I again choose this 10 values, press Ctrl, press Shift and then down cursor value. These two columns are selected. Go to Insert, go to Charts, this one. So oscillatory behavior, but some sort of increasing oscillation. So this is the case where your k is less than minus 1. Okay, so let's discuss them in terms of the Harrod model. So when k is greater than 1, then what happens? So as you can see, when k is greater than 1, your Gn, it increases without limit. So it is just increasing without limit and it becomes an ever increasing amount as your time passes. So that is the case when your k is greater than 1 and your Gn was b by b minus a whole to the power n into G0, which we have replaced by k G0, where k is equal to b by b minus a. When your k lies between 0 and 1, then you see that your Gn will decrease over time, and ever increasing, it is decreasing as the time passes. When your k lies between -1 and 0, you get that your Gn is oscillating around this baseline 0, and as time passes, this oscillators becomes a damp one and approaches the value 0. And finally, when your k is less than -1, then what you get is an explosive kind of oscillation around the 0 baseline with increasing oscillations. Now, what happens when your k is equal to 1? So, if your k is equal to 1, then b by b minus a equal to 1, which implies b equal to b minus a. So, your a equal to 0. So, if your a equal to 0, your Gn becomes b by b whole to the power n 0, and this gives you only G0. So, your Gn will be equal to G0 for all future time. And when your k is equal to -1, then your b by b minus a equal to -1. This will give b equal to minus b plus a, or 2b is equal to a. So, if you substitute it here, you will get your Gn is equal to, so a is 2b, so b by b minus 2b whole to the power n into G0. So, this gives -1 whole to the power n G0. So, your Gn will alternately becomes minus G0 and plus G0 period after period. So, for n equal to 0, it will be G0, for n equal to 1, it will be minus G0. So, it will be oscillatory between, rather a periodic kind of motion between minus G0 and plus G0. So, ultimately this Harrod's analysis, it implies that aggregate real output must behave as in this case 1 if the system is to move smoothly in such a way that the realized investment is always equal to the desired investment. So, summing up, in this lecture we have talked about an economic model, namely Harrod's model. So, from 3 basic assumptions, we derived the model and numerically shown various dynamics by changing the parameter values. In my next lecture, we will be talking about lake pollutant models. Till then, bye bye.